All right. I'm going to record it to the cloud. The cloud. Okay, so it's recording. And so I'm going to do a quick walkthrough kind of how Herbie works. And I think like executing Herbie and looking at some of the stuff afterward will be useful. So hopefully the recording will capture my screen well enough that you can recreate them. But you can also just email me and I'll tell you how to do so. Okay, so I've got Herbie right here. So I have a checkout on my computer. Let's go to the main Herbie branch. And here I am on the main branch. So this is like the most current version. And you can run it. Probably what it says on the website is to do this. Yes. But if you have a checkout, you can run your specific checkout like that by just giving a file name. I'm going to say report, and I'm going to run these tutorial examples. There are a whole bunch of benchmarks in the benchmarks repo, which you probably will want to make use of. These tutorial examples are three like really trivial ones. You see it's 1 plus x minus x, 1 plus x squared minus 1, and then this requires Herbie to like reassociate, and then they cancel perfectly. So you can run the code as such. So the first argument is the input, and the last argument is the output directory. This typically takes but a few minutes about a minute to run, but maybe it is recompiling something, so it'll take a little longer. It'll come. There we go. Every time Herbie runs, it prints a seed. This is very useful, so you can always add -- seed, and then that seed. And then when you rerun, it'll get identical results. That's not going to be super impressive for this specific input because it always gets identical results on these inputs. Like these are very simple Herbie benchmarks, but it's useful for other stuff. And then to view the output is HTML. So I usually do that by just starting Python's built-in web server. You can just point it to some file on disk. I'm not thrilled that I am showing you my email. So let's get it off the screen. This guy's already running a Herbie report somewhere. Did I literally put it at /temp/ow? Oh, okay. Looks like I already had a Herbie report at /temp/out. Okay, so we'll go with /temp/ow. There we go. So you can see a report here. You can see the 3 benchmarks that came in. The other stuff Herbie shows, this is sort of an input-output error plot. So the horizontal axis is how much error the original expression had, and the vertical axis is how much error the resulting expression had, which here is no error, 100% accuracy. And there's also a Pareto curve here with the initial value shown here. There's sort of captions.
The seed controls just the random
sampling
generation of inputs, right?
That's right, exactly.
Is there any way to see, like, does it matter really what inputs you get? Like, is the variability in the error measured that significant?
Yeah, well, we could look right here. So let's focus on the initial program. So if you like zoom way in over here, you'll see that there are these very faint circles. So each of these circles is a single input sample. And if you hover over them, it'll actually give you the error. So here is a specific error. This is index 2070. You'll almost never need this, but it's there. You can see the X value. It's some like large negative number. And you can see that this one has error 1. This one right here, index 4060, which makes sense. It's right around in the middle. And there are 8,256 sample points. Why that number? 256 is the training set, and 8,000 is the test set. So Herbie doesn't have access to those 8,000. It only has access to those 256. So here's an input. That value X doesn't really make sense. Actually, a lot of this doesn't really make sense. That's also not a sensible number of bits of error. So I'm not actually sure what's going on there, and I should fix that bug. So okay, there might be some kind of bugs here, but
is this just showing you the integer float though?
it might be something's weird with the on hover data, but these seem to be correctly positioned.
Yeah.
So basically you can see how many sample points there are. And the answer is like a good number. And as you can imagine, the variability isn't going to change that much. You can see that this thick line, there's some smoothing applied. So like clearly that smoothing is like eating away this sharp peak that happens at 0. And you see a little bit of that over here too. The sample points are the actual ground truth, right? The thick line is just for smoothing. For a case like this with a single input variable, it's usually very sharply defined. 8,000 points is more than enough. It's a couple per exponent bucket. Usually individual exponent buckets are not super interesting on their own. When you look at something with more inputs, well, realistically, this one is pretty accurate, but you can kind of see the sample points here. I can pull up a Herbie report from some recent run that is more complicated. And a lot of these will have more complicated expressions with more variables. So let's just pick one at random. Sure, this one. So you can see this one has a couple of variables, looks like U1, U2, and cos theta I. And then here, these are somewhat more random. So you can see that there seems to be some kind of dependence on U2, for example, which is interesting. When you got multiple variables, the smoothing often plays a bigger role because it's smoothing over kind of multiple dimensions, which is confusing. Like if I look up some of these quadratic benchmarks, so just the quadratic formula, you can see that the smoothing is pretty random. And what's going on here is there is some dependence on B2 because of some kind of cancellation problem that you can run into. But if you look at a different variable, like different values of A are independent of B2. And so you're mostly looking at like a constant difference, and then the smoothing obviously is struggling to deal with the random variation. It's not like being smoothed enough. So again, I would pay, the thick lines are useful sometimes. They're especially useful when it's one variable, but the ground truth here is all these little dots. So here, if we hide the Herbie's output, you can just see that there are a whole lot of dots at varying values of A that have very low accuracy, and also a bunch that have very high accuracy. You got a couple of points that are in between, and this is pretty typical. So the distribution of error is typically very heavy-tailed. Like you either have error and then your output is garbage, or you don't have error and then your output is good. And so if we look at something like we were looking at the expanding a square, I think all of these points down here I'd characterize as basically garbage. The reason they vary, right, is because for all of these inputs here, probably the floating point code returns 0, and the correct value is non-zero, and the variation in how much error it thinks it has is just variation in like, how close Herbie thinks 0 is to the correct. The correct answer is varying, but the error is basically the same. Basically, all of these have catastrophic error, and there's a couple of in-between points here, or just below positive -1, that have error in between, but that's like a very sparse set. So this is typically what sort of a Herbie result will look like. So shall we dive into the details of how it works? Okay, so there's this link up here. And this link is to the internal logging system that we've built, which contains a random collection of stuff, but it's what I use to debug. Sometimes things get added or removed. And so you can see that there are a whole bunch of phases inside of Herbie that are used. So I want to point out a couple of things. First of all, we've got this yellow and purple region at the beginning. So this is Herbie's setup phase. Then at the end, you've got this red and neon green phase at the end. That's like the finalized phase. And then you've got this green-blue phase with a little bit of purple in the middle. And you can see there's a repeating pattern of like green, blue, blue, pink. If you start scrolling, it becomes a little more obvious. You do sample, series, rewrite, eval, prune. 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 And then you switch to the finalization phase.
So this is the same loop that you have in your original paper as like the main loop.
Yes, exactly. So we still have this general structure. So there's this initialization phase, there's a main loop, which consists of 4 iterations, and there's a finalization step. I will say
we have
you
no
can
way to control the number of iterations of this loop.
you can say num iters 20. Eventually Herbie may run out of work. 20 might simply be too large a number, but you can see that when I told it to do 20, it did well. Okay, you can see that it did more iterations. 1, 2, 3, 4, 5. And then probably at the end of 5 iterations, it simply had nothing left to do. Yeah, you could see that of the kept iterations, they are all picked or done, as in it could not come up with any alternative that was intriguing for it. Like it, in that last iteration, it came up with 9 new alternatives, and it threw all of them away. Right? Total 9 new alternatives, of which 9 were pruned and 0 were kept. And there weren't any that it hadn't already investigated. So the only thing it had left was stuff it already used. I know that you've never seen this table before, but that's hopefully enough interpretation for what it does. Similarly, you can set it to do 1 iteration. And if we refresh,
at 4 at the moment, or like it will run until this saturation-y point.
Nope, the default is 4.
Okay.
And it'll usually hit 4. We have done a bunch of experiments, and basically there's usually a long tail of like pretty dumb ideas that Herbie has available to explore. So if you give it like 50 iterations, it'll often use all 50, and they typically won't make much of a difference. But they'll spend time. So here I ran 1 iteration, and this took less time, but you actually see that it produced the same exact output that it was producing before. So like realistically for this benchmark, you only need 1 iteration, and the default value of 4 is like 1 good idea and like 3 dumb ideas that it like explores and concludes are no good. And if you let it keep going forever, it turns out that it'll explore 4 dumb ideas and then run out of ideas.
So we kind of talk, iterations, are these like the iterations in the equality saturation algorithm, or
no? It's a whole different thing.
level. Yeah, okay.
Yes. So let me talk through the parts. We're going to talk through setup and iteration, and then tear down, or like finalization, right? So setup is pretty easy. Setup runs through these 4 phases. So the main one here is sampling. So what the sampling phase does is it needs to sample random inputs to the program. What do we mean by random? We mean random bit patterns. What do we mean by inputs to the program? The program has to be valid on those inputs. That's kind of obvious. Here for this benchmark, every single input is valid. It's just like multiplication and subtraction. But for something like the quadratic formula, where you have a square root, like validity is non-trivial, right? Like this discriminant part has to be positive. And similarly, it cannot divide by 0. So that's what the sampling phase does. We actually have a lot of information available on the sampling phase that you can like dig into. And you can see that to do the sampling, it uses a library we've built called Rival that uses interval arithmetic. And you can see here that it involves executing the various operations, addition, multiplication, subtraction, at various precisions out to like 2000 bits to do the sampling. The reason it needs that many bits is because this expression has high rounding error, near 0. And so if you want to get like a ground truth value, you might need a lot of bits. Why do you need 2000 bits? I guess because x can be 2 to the 2000. That's like about the biggest float. And 1 is 2 to the 0. So you might need 2000 bits to represent x plus 1. like fully. Probably it's the reverse. X can be like 2 to the negative 2000. That's probably the relevant one because it's near 0, right? So that this X is not rounded off, you might need about 2000 extra bits past 1. And then you can, do this and get some measure of accuracy out. So that's the sampling phase. That's the main thing Herbie does. There's a couple of
this is all double.
Yes, the default is double precision.
Exponent can be minus 256 or minus.
Yes. So you could say precision binary 32. And if I rerun that, I guess I put it in cancel like terms. So let's go find that one. Oh my God, I keep heading back and forth. Let's find cancel like terms. So this is a really simple program that just does some cancellation. You can see it likewise has error for very big values of X because the 1 is rounded off. And you can see that X here now terminates at 10 to the 38 because it is now single precision float. And that probably also means that these top out at like 500 bits, right? Because that's like the, I mean, these buckets are pretty big, so it probably tops out at 256. Okay, so that's the sampling phase. I'm going to go back to expanding a square because there's more stuff happening there. So this is the main thing it does. You can see that in total, so this little table shows you how hard it, the sampling process. You can see it samples about 8,000 total. And if you actually do the math, it's 4208 plus 1666 plus 2382, 8,256. So this is a test set of 8,000 points and a training set of 256 points. The training set here is pretty small because it turns out you don't need that many inputs. Like, you only need 1 or 2 points for Herbie to be able to figure out that there's floating point error there. It can overfit, but usually not too strongly. And the 8,000 sampling points is to give us, I think, like 1% accuracy. Like plus minus 1% on the accuracy measurement on average.
Your training set is distributed across the exponent range.
Oh, yeah. These are totally independent samples. Again, we are sampling basically random bit patterns and then evaluating them to high precision. And when you evaluate to high precision, either you determine that it's a domain error, or it might fail a precondition. You're allowed to specify preconditions, or we'll get an output out, and then we use that output. The sample phase is paired with this analyze phase. All that the analyze phase does is it tries to do this test for validity and preconditions. So here it's pretty dumb. You can see that after the first iteration, it has found a subset of R where the input is valid 100% of the time. So that's because all inputs are valid for this program. But for something like quadratic, you'll see that Herbie will spend some time recursively subdividing the input until it has, basically to improve its probability of sampling successfully. So, I mean, in this case, you can see that it is probably just spending a lot of time like looking for the region like b squared minus ac, where like the discriminant is negative, and like splitting that into like axis aligned rectangles and not sampling from the bad ones. So analyze is just there in service of sampling, which by the way is how we tune it. There's some like fixed number of iterations. You can actually change the number of iterations. I would not, because it doesn't matter that much. You can see that these like last iterations make a pretty small impact. Like they increase the probability of a successful sample by like 5%. These are much faster. You can see it's about 10x faster. So each iteration is probably quite a bit faster. Anyway, you don't need to worry about that. That's probably not the part that's of interest to you. One part that might be of interest to you, though, is pre-processing. So let me find a benchmark that would be good for pre-processing. What is a what's a benchmark where this is relevant? I think I looked at this one earlier, and it was relevant. Yeah, okay. This is a great example of something where pre-processing is relevant. So if you take a look at this benchmark, you will see two interesting facts about it. First of all, you can see that focus on the variables P and R. First of all, you will see that the signs of P and R don't matter very much. They can change this plus to a minus, but like if you flip both signs, that doesn't affect anything. You'll also see that if you swap P and R, this expression is unchanged and this expression is unchanged. So these are identities that Herbie can detect of a expression. Here, what it can detect is that P and R are symmetric variables. And if we go into the metrics here, you will see under pre-processing, it detects two identities. First of all, the sign of Q doesn't matter. And second of all, P and R can be swapped. The name here, sort, is because you can sort P and R. And similarly, you can detect that Q is an absolute value. Let me show you how this works in the code, just so that you get a sense of it. I'm going to go into source core preprocess. And if we skip a bunch of stuff, we can find the find preprocessing function. I have a blog post that's linked in the code that describes the general idea. But basically, we take the specification, the real valued expression that the program corresponds to. And then we have these three types of identities we look for: even, odd, and sort. And if you look at these, identities are just a variation of the program that we want to know if it's equal. So for example, to check if we can swap A and B, we construct the program with A and B swapped. And then we're going to check, are those equal? So we build an egraph, we run a bunch of rewrite rules, and we check if the original specification is equal to the munged one. So if f of AB is equal to f of BA, which we do by constructing f of AB and constructing f of BA, that part is right here. Constructing f of BA, replacing A with B and B with A. And if they are equal, then we know that the corresponding identity, sort AB, is valid for this program. And a big part of making Herbie efficient is making sure that we're always kind of doing things in batch, so that you can see what we actually do here is we test all identities at the same time. So there's going to be like n squared sort identities. So here we iterate through all of the pairs, right? And there's going to be also of the even identities, which is like replace x with negative x, and odd identities, which is replace x with negative x, and also negate the output specification. So Herbie will look for these identities, and when it finds these identities, it can do something useful. So if we go back to the details, you will see that in the original program, we have P and R. But in the output program, we actually have max PR and min PR. So it switches variables from thinking about P and R to thinking about the maximum and the minimum. It sorts them. So you can see there's actually no P and R in this program at all. There are only min and max expressions. And that can be useful, right? Because Herbie can now consider only a subset of points where P is less than R or something like that, right? Similarly, here it knows that Q, the sign of Q doesn't matter because Q is squared. So you can see that throughout the program, we only have the absolute value of Q. The actual value of Q is never used. And the reason that's handy is that you can see that we actually end up constructing a branch expression over Q. So we're comparing Q to some minimum and maximum values, and just eyeballing the values, we're probably protecting against overflow. And it's convenient that Q is absolute valued. If we didn't do that, we'd have, what, 5 branches, I assume. So we get to save a little bit. And that that's helpful because if we had more branches, then Herbie has some regularization there. So that would be useful. Similarly, the minimum, the maximum might help it discover in some cases and kind of rewrite. When Herbie detects these identities, you can see that there's a pre-process step in the beginning that finds all applicable identities for this expression. And then there's also one at the very end here, one of the last things Herbie does, where it checks whether it wants to keep them or not. And I think the logging for this is kind of broken. We used to do this globally, but we now do this expression by expression. But it seems like in this case, it at least removed the, did it? It says it might have removed one, but I don't see it removed. So probably the logging here is just broken and we should figure out what the hell's going on. Work in progress. Okay, so that's the setup step, and that is the first place where Herbie uses egraphs. It is using egraphs to detect these identities. I think these identities are a fairly small part of Herbie. One thing you can do is you can disable them. So in Herbie, we have this system of command line flags that can turn things on and off. You can see them here in config.racket, but also documented on the website. It looks like we actually don't have a way of.
When the pre-processing discovers these identities, where do they actually get used? Like, do you then replace the running program with?
Oh, yeah. Great question. Let me show you the code. So you could see that we first find all applicable pre-processing, and then we use that to modify what we call the P context, the set of sampled points. So for example, in this benchmark, we're going to sample a whole bunch of input points. But then we're going to determine that P and Q are sortable. Right? So I might have points where P is less than Q and some points where P is less than R, some points where P is greater than R in my initial sampled set.
Yeah.
What I'm going to do is I'm going to sort P and R in all of my input points. So the rest of the program is only going to look at the sorted values of P and R, this like max P and R and this min P and R. So like quite literally, I change variables. You will notice that the only operations that Herbie is willing to do on input variables is like sort them and negate them. And that's because these are exact operations. So this doesn't do any kind of floating point stuff. Maybe it would be cool. We've thought about like normalizing vectors. That's another thing that could be useful, like in floating point world. But that's tricky because that introduces its own floating point error. So like a big question, I guess, throughout Herbie is Herbie's going to make changes to the program. And then it's going to test whether those changes are good. And if those changes are bad, it wants to back out. Right? But that's also expensive to do because you got to like do more evaluation. So this pre-processing step is irrevocable. You like always apply all the identities you have. We will like clean up supposedly the ones that don't matter at the end. I don't know why it's not doing that here, but whatever. Yeah, like it matters, right? So it matters that it's exact because Herbie can't undo that step.
But then in proposing this like T0, that's just what Herbie has learned, right? This is
the T0 is from, well, you can actually see that it's just this sub expression here, this P minus R.
Sure.
With that variable replacement. But yeah, that's from the core of Herbie. So let's look at this core of Herbie where it actually does the iterations. I was gonna tell you that you could turn pre-processing off, but it looks like you can't. I'll add a flag so that you can turn it off. I don't think like you necessarily want to, but
yeah, I think
we generally like to
want to turn it off for our evaluation because we won't have
let's just go here and say issues, new issue, no flag to turn off pre-processing.
And can regime inference be be turned off?
Yes.
Okay.
So you mentioned regime inference. Let me just quickly talk about it, since my promise was to talk about all the phases of Herbie. Regime inference is one of these things that happens at the end. So if we scroll down to the tail end, you can see that the tail end of a Herbie run is regime inference, B search, which happens several times in succession, and then derivations, and then this pre-processing step. I already showed you this pre-processing. This is like a cleanup where Herbie tries to keep only the useful pre-processing steps. Apparently unsuccessfully. I should look into that. The regimes, this is pretty much unchanged from how it was in the Herbie papers. So basically, Herbie will start with a whole bunch of input expressions. So here you could see this is a much bigger benchmark, and you could see that at the end of the 4 iterations, it seems to have 35 expressions that it is interested in. They are printed right here. You could see that some of them are purely algebraic rewrites. Others have these approx nodes in them, which indicate that at some point Herbie did a Taylor series approximation. Here's a bunch more with approx nodes. And they have varying accuracies. They also have varying costs. So Herbie will attempt to do like a Pareto curve of like highest precision at any cost. And then this regime inference pass and attempts to combine different of those expressions. So you can see that it's slightly bigger than these 35. It's anything that Herbie thought was a good idea at any one point. So it combined 84, considered 84 expressions, and it found a combination of 3. And we can actually see that here. Here's a combination of 3 different expressions that Herbie came up with. 1, 2, 3. And then slightly lower later, it looked at a batch of 71 to find a lower cost example. So it looked at another batch of 71, still found 3, and that's going to be our second alternative, still found 3, but you'll see these are somewhat cheaper. It doesn't have a division, I guess, and who knows what else. And then to go even cheaper, so why did this number decrease? Because it needs to throw away anything that's more expensive than the ones that are used here. So similarly, of these 71, if you throw away everything that's more expensive than any of them, you have 74 left. For that, it had 2. And so that's going to be our alternative 3 with 2 options. And you can see alternative 4 with 2 options. And your cheapest alternative is usually some garbage like this. I mean, this is obviously minimally useful. And Herbie cops to this. It's like, wow, this is like super garbage. It's not accurate at all, but boy, is it fast. Herbie will typically say something like that. So that's the regime inference pass. The way regime inference works is it tests different branch conditions, P, Q, R, possibly some random expressions it's come up with over the process of optimizing Herbie. For each of these, it'll look at what's the optimal way to split it up. So here, splitting by Q gives it 3 branches at 70.6%, and that is probably this first alternative. The numbers don't match up because we have this like test versus training set. And then you can see, other variables are worse. Then it considers, then it like repeats this for the next batch. So that's why these numbers decrease as it goes up. Why is it decreasing? Because in Lisp, it's easier to add to the front of a list. Okay, so that's this regime pass. The B search pass is very similar. Basically, it just looks at these branch conditions. So it's about this number, 8.5 times 10 to the negative 126. Like, where to get that number? Well, it got that number somewhere in this range. These are 2 specific sample points. And then it binary searches between them for some number of steps. I forget how many, maybe 8 or something like that. And then it picks the shortest number in that range. So probably it like narrowed it down to like 8.4 to 8.6, and then it picked 8.5 in the middle. So this B search, this is the same thing as regimes. 1 second, let me Our daughter woke up. Okay, so that's the regimes and bsearch pass. This derivations pass, this is purely for display, but this is doing those egraph proofs. So those are what show up over here for the step-by-step derivations, so that you could see like the actual sequence of rewrites that Herbie made. So that's this tail end. And so what's left is to talk about the inner loop. So I'll pause here and then we can.
If we disable regimes, we get a single expression at the end.
You will get multiple alternatives, but each of those alternatives will be one expression with no if statements.
Yeah.
Yes. We could. I don't want to do the tutorial because that'll be boring. Maybe I'll do the quadratic benchmarks. Hamming, quadratic, and then I can do disable, and then the config parameter is oh no, I should look at default, not deprecated. Reduce regimes. So let's disable reduce : regimes.
Where the difference between that and branch expressions is?
Branch expressions is you're allowed to branch on expressions, not just variables.
Okay.
If you disable regimes, then branch expressions won't do anything.
Yeah, I see.
Let me go this place. Oh, she is upset. Cool. So now you can see that there are. It will sometimes insert if statements. But these if statements are typically kind of lame. Oh, no, this is the developer target. I see. Herbie literally couldn't do anything without branches. So there are no alternatives at all because the best thing it could come up with was the initial program.
Nice.
So, I mean, that's kind of lame, but
yeah.
Do you have anything here? Yeah, okay. So here, it did have an alternative. Its best idea was like you can use an FMA. It's not a very good idea, but it tried. You know, it's probably minutely more accurate because it's showing this in green. It might also be very slightly faster. It's obviously not very good, and that's because it's not allowed to do regimes. So you can see here, there's no red at all, so no regimes phase, right?
Yes. Cool.
Okay, so let's talk about the main loop then. The main loop consists of 5 phases. They are sample, which we actually call evaluate. So evaluate, series, rewrite, eval, and prune. I think of this as 2 groups. The first group is sample, series, and rewrite. These are 3 approaches that Herbie pursues in parallel to try to improve a program. So let's start with sample. Sample is really easy. I can demonstrate it with this XKCD derived benchmark. XKCD217 is this benchmark that points out that e to the pi minus pi is really close to 20. So this benchmark is 20 minus e to the pi minus pi. What's interesting about this expression is that it is a constant. So instead of doing any kind of funky rewriting, which would struggle to find a way to evaluate this more accurately, Herbie instead uses this sample phase. So what does this sample phase do? It literally just evaluates the expression in high precision and blets that out as a constant. So what did it do? It evaluated real constant to the correct answer and like spits it out. Easy stuff. It's probably not doing very much. We added it and it did some minute amount and it was very cheap. And it's cool that it can do examples like this well because we see users putting that in. But this is not super interesting. I believe you can disable it. So you could do disable, generate, evaluate. And that will just disable this phase. I don't think it does anything on quadratic, so I'm not going to bother running that. But, well, I guess I can run it, and then you could just see that that phase is gone from the timeline. I'm guessing a lot of your experiments will involve disabling some of these phases so that you don't have to, so that you can compare like with like. Yeah, so now I've rerun it, and now there is no sample phase here, just series, rewrite, series, rewrite. Okay, So that's this first sample phase. Let's look at our next phase in question. There is the series phase. So this one is pretty obvious. It takes series expansions. The way it works is a little complicated. They're not quite series expansions. They're this more complicated thing. But you probably don't care. You probably just don't want them. So you can disable those as well. So you can go in and you can say, let's turn regimes back on. Otherwise, Herbie will be sad because it will not be able to do anything. But I can disable generate Taylor. You might wonder, why is it series on the website and Taylor in the code? I need to just rename stuff, man. This is how it goes. So Taylor, this proofs is the derivation branch. I should rename all these to be uniform, but whatever. So Taylor and evaluate, those are those two phases. So now if I refresh here, you will see that there is no series phase either. And if we go back to the results, you will see that, should I turn regimes back on? I can't do anything without regimes. That's interesting. I should figure out why that is. But you can see that it's doing rewrites, but it is not at any point applying Taylor series expansions. Yeah, so this last, okay.
If you were to like roughly quantify it, like how much do you get from each of the three? Like you said, sampling basically nothing. Taylor versus
rewrite is obviously the biggest one.
Okay.
Sampling is basically nothing. Taylor, okay, there's two parts to this. One is Taylor is often a convenient way to simplify polynomials.
Yes.
It is not doing any Taylor series approximation there at all. It is simply using it to do like a normalization step. And that's because Herbie puts the egraph on a very tight leash.
Mm-hmm.
The egraph is very small because we want it to be fast.
Mm-hmm.
So that is a thing that Herbie uses Taylor for a lot. There's also a bunch of benchmarks that just it does not solve without. Quadratic, it should be able to make some progress on. I should look into what's going on there. But there's a whole lot of benchmarks where like Taylor is obviously useful. Like if you look at the outputs here, you'll see this is the initial program. This is obviously not equivalent. So this branch here, that's got to be Taylor series. And this one here, that's also got to be Taylor series. Just because like, yeah, I mean, think about it. Like, you know, there's no way to like get rid of the square root by pure rewrites. It had to like approximate it away somehow. Okay. So one thing I want to point out about the Taylor phase before we fully leave it in the dust is that if you pull up the series phase, you will see this little iterations chart. And this iterations chart is actually showing you an egraph run. It ran one iteration with 1,000 nodes, and it stopped because it was limited by number of iterations to one iteration. And the reason that happens, you can see this in patch.racket, where we run Taylor. Our Taylor series expander works on real expressions. So to do a Taylor series inside run Taylor, we first compute the Taylor approximation as a real expression, and then we lower it to floating point operations. So you can think of this as instruction selection, like in a backend of a compiler. Our instruction selection pass uses egraphs. That is because here is what a backend looks like. You go into platforms and you look at, say, c.racket, which is the default platform. You can see that a platform is a series of floating point operations, including their floating point implementation. Like here, floating point pi is a constant function, which is the value of pi cast to a single precision number, plus a specification. So when Herbie has a real expression, needs to convert it to floating point, it basically uses rewrite rules of the form like, hey, if you have this real expression, you can rewrite it to this floating point expression. Or more interestingly, if you have this hypotenuse function, you can rewrite it to a call to hypot. So this instruction selection, you know, you can think of this as like tree matching, but it's using an egraph It's still basically doing tree matching. I guess this is just us being lazy. But this is going to be more useful when we talk about rewrites, because rewrites are going to do instruction selection and actual algebraic rewrites where the egraph will have interesting structure. Okay, so let's go to this rewrite phase. This is obviously the one called rewrite, and you can see here there's a lot more stuff going on. So let me pull that up in the code. If we look at run RR, which is here, you can see that it runs a more complicated schedule. So its schedule has 4 parts here. It takes as input floating point expressions. So it first lifts them to real number expressions. Then it applies rewrites up to a node limit. So I believe the node limit is 4,000, which is very small. Then there is this phase called unsound, which I'll talk about in a moment. And then there's a phase called lowering, and that's that instruction selection pass. So the lift and the lower, they're kind of opposites, right? We start with floating point, but then we convert it to real to do the rewrites, and then we convert back to floating point at the end. And this, we look here, you can see that schedule. Here is the lifting phase, 1 iteration. Then you got the rewrite phase, which is 3 iterations, and you see it terminates, presumably because it hit 4,000 midway through its 3rd iteration. Then it has an iteration of unsound, which seems to add about 300 nodes. And then here's 1 iteration of lowering. So there's like an incomplete iteration in the middle here that you're not seeing. So it did 3 full iterations. And you can see that over the iterations, as you might expect, the size of the egraph grows exponentially. Again, just kind of as is standard. And that's why we limit it, basically. Our set of rewrites you can find in the code base. It is called rules.racket. And you can see the rewrites here. Herbie initially had something much weaker than an egraph. It had a directed, somewhat exhaustive rewriting system. And so there's actually a lot of duplication in the rules. You could surely compress the associativity rules down to fewer of them. But that's actually not why the egraph explodes, because the egraph is good at like compressing multiple sequences of those. But there's a lot of rules here that can lead to explosion. You know, there's a bunch of stuff with manipulating polynomials that can often be very expensive. And then we've got like difference of cubes and difference of squares formulas that can produce big polynomials, all sorts of fraction manipulation, a lot of stuff involving how the FABS function works, which is actually very important in Herbie. Cube roots, min and max, exponentiation, product rules for exponents, et cetera, et cetera. We can keep scrolling. A whole bunch of trigonometry rules, a lot of trigonometry rules. There's a lot of trigonometric identities. Hyperbolic trig, which is a lot of very similar identities to the original ones. And so that's kind of the set of rules. I believe there's about 200 rules in total, maybe 250, something like that. So it's a pretty large number. And some of these just inherently cause big blowups. So like, for example, flip this rule takes any subtraction and constructs the difference of squares formula, a squared minus b squared over a plus b. It's a lot of subtractions. So this tends to produce a whole lot of nodes that then Herbie could spend like a lot of time thinking about the numerator and like how to do stuff to it. I mean, this is the usual trade-off with egraphs, right? You write a lot of rules, and most of them are dumb, and you let it go. Again, we keep it on a pretty tight leash. 4,000 nodes is not a lot. Herbie gets better if you give it more nodes, but it also gets slower. Is there any particular reason we picked this number? Nah. It's just been that way for a while. Like, yeah, like it's a trade-off. You could give it more nodes. One big problem we have is that our extraction phase from the egraph. Oh yeah, and the egraph in question is egg. Herbie has an optional egglog backend that you can switch to. At the moment, the egglog backend is much slower. We know why, and we're working with the egglog folks to fix it. The long-term dream is to switch to egglog entirely. At the moment, though, egglog is both slower and worse. So until we fix that, we're not going to switch to it. But the two backends work very similarly, except for the extraction phase, where egglog allows us to do more in egglog and less in racket. Basically, there's like a type-directed extraction phase that we have to implement in racket for egg. We are hoping to one day switch to egglog, and then egglog will ideally be way faster, and then we will just bump the number of nodes to like 20,000 or something, or 100,000. I don't know. So this is the main place it's used.
And the sound annotations, what do they mean within? You have various like commented.
So let's talk about that. So soundness. So once we've talked about the egraph, we got to talk about a couple of classic egraph questions. What are the expressions? What does equality mean? Right? Like the classic. So expressions are easy. I mean, you know what a math expression is. And equality for us, naively, it means that the left-hand side and the right-hand side are equal. So let's look at this one. C plus B over A is equal to C times A plus B quantity over A. Fine. Okay. Yeah, that's good. Right? We're doing some kind of like move the C into the numerator of the fraction. And all of these rules, we do have random testing for the rules, just like sample inputs and make sure that the results are the same. You can see that code in test rules. It's pretty straightforward. Sample input points for P1 and P2 and check that the computed values are equal. It's like a 50-line file, 65. The tricky part of equality is what do we do about invalid values? So there's a couple of ways to do it. Let's consider a couple of interesting rewrites right here. One rewrite here is A plus B to B plus A. Here, the left and the right-hand sides are clearly valid on exactly the same set of points. So these are definitely good. These are definitely sound. Literally for all inputs, they produce the same output. If for some reason A plus B is a domain error, then B plus A is also a domain error, right? Like if A is actually some kind of square root operation, well, we're going to have the same error on the right-hand side. But that's not good enough, though, because what about the following rewrite? Here, the left-hand side can have domain errors that the right-hand side doesn't. So there's an input, A equals 0, on which the two sides behave differently. Okay, and then here's my final rewrite. Hopefully you can parenthesize that correctly in your head. Okay, so these three behave in different ways. This one, I will say validity same. They are literally valid on the same exact set of points. This one, the validity is a superset. The right-hand side is valid on more points than the left-hand side. And then here, the validity is subset. The left-hand side is valid on inputs where A equals B, but the right-hand side is not because it divides by A minus B. In Herbie, we say that this is okay and this is okay, but this is unsound. This is not the only way that you could do it. You could instead choose to do it this way. This is very easy to justify. In this case, you're saying our mental model is that when you have an invalid input, you produce a special error value, call it nan, and then you just have to be equal on all inputs, right? That's a world of total functions that have to be equal on all inputs. So this is really simple to justify, but it bans rewrites like this. The left-hand side would compute to nan, the right-hand side would compute to 1. Unfortunately, we want these rewrites. There's a lot of these rewrites. like more than half, I think, of rewrites at some point we counted, have some kind of principle like this. So our mental model for validity is actually slightly different. We say that there's some kind of side condition, which is that the initial, we only consider inputs where the initial egraph was valid. So if you have a square root x expression in your original egraph, then we're just assuming that x is positive, and we don't care about negative values of x. So this initial egraph matters quite a bit. But then we preserve that validity through all our rewrites. We will never add expressions that are equal where the original thing was not. Check if that's nope. So that's our mental model for how the soundness works. So then what do we do about rewrites like this? Where it's like this end up being tricky. We want this rewrite too. So for rewrites like this, we add a special operation that we call sound division. It works like you expect. Oh, yeah, sound division. You've got a numerator, a squared minus b squared. You have a denominator, a minus b. But then you have a fallback to use if the denominator is 0. So now this is the sound rewrite. Now the left-hand side and right-hand side are equal on all inputs. In the rare case that a equals b, then we return a plus b on the right-hand side, which is also what we compute on the left-hand side. Positive, this rare rule is sound. Negative, we had to invent a whole new function, sound division. There's no reason to think that like there is a sound division function on the computer in question. So at the very end, we have 3 unsound rules that do the obvious thing. Turn sound division into unsound. Turn sound exponentiation into unsound. And turn sound logarithm into unsound. Well, these work in the same way. There's a fallback argument to use when it would sound. And that's bad. An unsound rewrite rule, if used too crazily, could give you invalid merges. Like here's basically the proof. 1 is equal to 0 over 0, because anything over itself is equal to 0, is equal to 2 times 0 over 0. That's just constant folding, equals 2 times 0 over 0. That's associativity, equals 2 times 1 equals 2. Bad news bears once you prove that 1 is equal to 2. So basically, here's our big idea for soundness. We run these unsound rules, but we run them right before extraction. So we will never do additional rewrites on sound division, assuming that it is actually a normal division, right? So once we construct one of these sound division operations, we're not going to do any further rewrites. We don't have any rewrite rules with a sound division on the left-hand side. That'll just stick around untouched until the very end of the egraph. And then right before we do lowering and extraction, we will treat those sound divisions like regular divisions for the purpose of extraction. So that's the idea there. Basically, you never do further rewrites on these sound divisions. They're kept in place, and they're only treated as regular divisions for the purpose of constructing floating point operations at the end. So that is our notion of soundness and extraction. You can see the egg code. I will say that the egraph, that the egglog version, generate egglog, which you can turn on like that, is a lot easier to think about. Just because, oh yeah, you can enable egglog backend and then enable dump egglog. And what Herbie will do when you enable dump egglog is it will crash. Okay. Great job, guys. Do I need to fix it or did it? Well, great. What it's supposed to do instead of crashing is, oh, I see it crashed when generating the output. Okay. Real great, folks, real great.